Hello, it's Rick Powell here at Nanoprobes again, introducing our Click Nanogold labeling reagents, which will let you label biological molecules with our 1.4 nanometer and a new 5 nanometer covalent gold nanoparticle in vivo using a bioorthogonal click reaction. Click chemistry is the reaction between an azide and an alkyne to give a triazole. And this is a reaction which isn't found in nature. The original click reaction was catalyzed by copper 1 ions, and it was known as a copper-catalyzed azide-alkyne cycloaddition, or CuAAC reaction. What makes it click? Well, it proceeds under physiological conditions. There's no cross-reactivity with tissues or cells because this reaction doesn't happen in tissues or cells naturally. It's a fast, efficient reaction. The reagents and the products are non-toxic, and it can be used in living cells and tissues. Click reagents are one of a class of labeling reagents known as bioorthogonal labels. Others include the snap and clip tags, the halo tag, and the flag tag. And they're known as bioorthogonal labels because they use reactions which don't occur naturally, and therefore they can be used in living cells and living tissues without any risk of cross-reactivity with endogenous components. They're non-toxic and biocompatible, stay reactive during long experiments, and can be used to tag components in dynamic processes. Here again is the copper-1 catalyzed CuAAC reaction, or copper-catalyzed azide-alkyne cycloaddition CuAAC reaction. And here's our Nanogold labeling reagents that use this reaction. First of all, Mono-Azido Nanogold, which labels biological molecules that are modified with alkynes. And this consists of the 1.4 nanometer Nanogold gold nanoparticle substituted with a single reactive azide group, and it targets alkyne modified proteins or nucleic acids that have incorporated synthetic alkynes. And this proceeds both by copper-catalyzed and copper-free click reactions. The second product in this line is our Mono-Alkyne Nanogold, which targets azido-modified biomolecules, such as proteins or nucleic acids with synthetic azides incorporated. And this contains a single alkyne group which reacts with the azide. The other flavor of click, more recently developed, is the copper-free click reaction, which is known as the strain-promoted azide-alkyne cycloaddition reaction. This is great because it eliminates copper, and copper can be cytotoxic, so this eliminates any risk of cytotoxicity during click labeling. And this simply proceeds under physiological conditions at pH 7 to give, as before, a triazole conjugate, and the extra reactivity is engendered by using a strained alkyne, which reacts more readily with the azide. To complete our range of click reagents, this is our 1.4 nanometer mono DBCO-Nanogold, and that contains the strained dibenzocyclooctane moiety, which reacts with azides under physiological conditions in the absence of copper to do copper-free click labeling. With this line of click reagents, we're introducing a new larger size of Nanogold, 5 nanometers. These are the first 5 nanometer covalent Nanogold labeling reagents. And we include in this lineup DBCO, Azido, and Alkyne 5 nanometer gold. The features of these reagents include they're bioorthogonal, so there's no cross-reactivity and no background labeling. Mono-Azido Nanogold works for both copper-catalyzed and copper-free reactions. They're stable and biocompatible. They're soluble but uncharged, so there's no binding to proteins or nucleic acids that have charged domains. They're well tolerated by living cells. You can use Nanogold reagents and conjugates for live cell labeling without disrupting cell viability. Ultra-high resolution. Nanogold goes right on the target site. And you can use high-resolution electron microscopy to see targets at macromolecular resolution. They can be optically visualized using silver or gold enhancement for light microscopy. And using this on blots, it's a super sensitive detection method. You can see as little as 1 picogram of target IgG. Undecagold reagents, which are smaller, 0.8 nanometers in diameter, are also available for ultra-high resolution electron microscopy, such as single particle analysis with image analysis. Applications of these Click Nanogold reagents include labeling components of vital processes in living cells, and you can ignore endogenous components like biotin or cross-reactive proteins. High-resolution labeling of subunits or molecular sites. Just incorporate the corresponding reactive azide or alkyne. No antibody or probe is required. Multiplexure labeling. You can add a click reaction to detect an additional target if there's no suitable antibody or probe that binds to it directly. Click Nanogold, to sum up, is a bioorthogonal label. There's no cross-reactivity or background binding in living cells or tissues. Stable and biocompatible, well tolerated by living cells, provides ultra-high resolution, and when used with silver or gold enhancement, you see highly sensitive optical visualization for light microscopy and blots. And for ultra-high resolution, specialized electron microscope techniques, you can use the smaller 0.8 nanometer Undecagold. Now, to use these reagents most effectively, it's best to plan your labeling. Usually the separation method determines the stoichiometry. We recommend separating Nanogold labeled molecules by gel filtration liquid chromatography. So usually you would use an excess of the smaller component because that's going to be more easily separated from the larger conjugate. And that makes the larger of the two reagents the limiting reagent, so it's used up and there isn't any unused reagent to separate. For molecules smaller than Nanogold, for example peptides, you'd usually use an excess of the smaller molecule, maybe 5-fold to 10-fold. And for molecules larger than Nanogold, such as antibodies or proteins, you'd use an excess of Nanogold from 2-fold to 5-fold. Nanogold's about the same size as a protein of 8 to 10 kilodaltons molecular weight. Its molecular weight is 15,000, but its size is smaller because of the molecular weight contribution from heavy gold atoms. The 5 nanometer Nanogold is larger than this. It's about the same size as a Fab prime fragment, or about the same size as streptavidin. If you're doing Click Nanogold labeling using the copper-catalyzed CuAAC reaction, the copper-1 catalyst is generated in situ from copper-2 by mixing copper sulfate, tris-3-hydroxypropyl triazolyl methylamine, or THPTA, which stabilizes copper-1 ions, and sodium ascorbate to reduce copper-2 to copper-1 and initiate the reaction. The procedure is given here. Now I'm not going to go through this in full because we don't really have time, but at the end of this presentation there'll be a link to download the slides. You can download the slides and read the full step-by-step procedure from those. So continuing, mixing the reconstituted Nanogold labeling reagent with the protein to be labeled and then adding to the copper-1 mixture. Incubate on a shaker with gentle agitation for an hour and then separate. And using the smaller 6 nanomole sizes, you can conduct the reaction on a smaller scale or do several small aliquots. And again, same procedure, just smaller scale. And here are some references for the copper-catalyzed click reaction optimization. And again, if you want to look these up, the best approach is download the slides at the address given at the end of this presentation. Now for strain-promoted labeling, copper-free labeling, or SPAAC labeling, here's the procedure using 30 nanomole sizes of these, and you can use, given the procedure here for the mono-DBCO nanogold, but the same procedure is used for Mono-Azido Nanogold labeling of molecules that have been functionalized with strained alkynes. And the procedure is the same except that the reactive groups have been reversed. And again, prepare a 500 micromolar solution of alkyne or azide modified molecule to be labeled in 0.1 molar phosphate buffer, pH 7. And planning your labeling, you'd usually prepare smaller amounts of larger molecules so that you have, say, a 3-fold excess of nanogold. About a 1.5-fold excess of nanogold if you're labeling something which is about the same size. And if the protein that you're labeling is smaller than nanogold, significantly smaller, then you prepare a larger amount so that you get a 3-fold excess of protein. And again, this is an even simpler procedure because it's simply mixing them at room temperature, vortexing to make sure they're dissolved, and then agitating gently for an hour, or incubating at 2 to 8 degrees Celsius overnight in the fridge, and then separate the next day. And again, here are some references for the strain-promoted or copper-free click labeling reaction optimization. Now, how do you separate the nanogold conjugate? As I mentioned before, gel filtration is the preferred method. Separates larger conjugates from both unlabeled conjugate biomolecule and unreacted nanogold, as well as from larger multimers. And the best approach is to make the larger reagent the limiting reagent, so it reacts completely and there's none left unreacted. Ideally, you should have a size difference of at least a factor of 2 between the conjugate and the smaller reagent used in excess. And this works well on standard liquid chromatography, and usually doesn't require HPLC. To set up the separation, equilibrate the column for 2 column volumes before you inject the reaction mixture. The injection volume should be at most 5% of the column volume. For best resolution, make that smaller. You can use a centrifuge filter, like a Centricon from Millipore, to reduce the volume before the injection, if necessary, or use a larger column. Monitor at 280 nanometer wavelength for proteins, or 260 nanometers for oligonucleotide conjugates, and check absorbance at 420 nanometers for the 1.4 nanometer nanogold, and 520 nanometers for the 5 nanometer nanogold. Monitor visually. The 1.4 nanometer nanogold and its conjugates are brown, and the 5 nanometer nanogold and its conjugates are red. Here's an example of the gel filtration separation of 1.4 nanometer nanogold. And on the left is what you would see in the column, as the nanogold labeled FAB prime in this case separates out from unbound excess nanogold and smaller molecules. And both those nanogold bands are brown. And on the right, here's a colored chromatogram from this. And as you can see, the first species come out of very small amounts of aggregates and nanogold Fab prime 2 conjugates, which are all larger than the desired species. And the first major peak is nanogold FAB prime, the desired conjugate. As you can see, that's well separated from the large peak that follows it, which is unbound excess nanogold. Here are some of the gels that are best for different separations. For antibodies, then Sucrose 12 or Superdex 75 works well, depending on whether you're using the complete IgG molecule or a smaller fragment. For proteins, you can use Sucrose 6 or A1.5M from Biorad for large proteins, or Superdex peptide or PG30 for small proteins and peptides. For very small molecules, use GH25 or a similar desalting gel. You can also use spin and gravity columns. And these are available with a variety of molecular weight cutoffs for different sized molecules, different sized proteins and nucleic acids. And again, these are available on our website, and the links are given in this presentation. So please download the slides and use the links to find out more details. Gel electrophoresis can also be used to separate nanogold labeled biological molecules. We suggest, though, that you use caution in interpreting the gel electrophoresis results, as gel shifts may not be good indicators of labeling. Nanogold has a nominal molecular weight of 15,000, but the gel shift may be much smaller. Use non-reducing gels. Thiol-containing reagents like diethiothreatol can break down and degrade the nanogold particle quickly. Detect each component separately to confirm the labeling. Run 2 lanes. Stain one with silver or gold enhancement to detect the nanogold, and stain the other with a protein stain like Kumasi blue. Bands that show in both lanes are the conjugate. Silver or gold enhancement are highly sensitive. Monitor these carefully. A tail may develop behind the band and obscure resolution if you let them go for too long, so make sure you wash the reagents off as soon as development is sufficient for you to see the results. And finally, avoid protein silver stains. This is a different chemistry to silver enhancement and won't give the same results. Nanogold labeled oligos can be separated with ethanol precipitation. Nanogold's highly soluble in ethanol, and you can use the ethanol precipitation to precipitate unlabeled oligonucleotides. And depending on the size of the oligonucleotide and its composition, higher ethanol concentrations may precipitate labeled oligonucleotides while removing unbound nanogold. 5 nanometer nanogold is also highly soluble in water and water ethanol mixtures, so use ethanol to precipitate and remove unlabeled oligonucleotides. Nanogold labeled oligonucleotides can also be separated by reverse phase chromatography, which separates unlabeled oligonucleotide, unconjugated gold, and conjugate. We find that the best results are obtained with a butyl or C4 column, eluted with a gradient of 0 to 70% acetonitrile in 0.1 molar triethylammonium acetate buffer at pH 7. However, a word of caution. Oligonucleotides vary enormously in their separation properties based on their size and their composition, and likewise their nanogold conjugates. So if you don't get great results, you might consider hydrophobic interaction chromatography for better resolution, or modifying the pH or the gradient or the column functionalization for a longer alkyl chain for the best results. Gel electrophoresis will also work for oligonucleotides. Like proteins, we recommend you divide the reaction mixture in 2 and run 2 gels in parallel. Treat one with a standard DNA stain such as ethidium bromide to visualize the DNA species, and develop the second with silver or gold enhancement to visualize the nanogold. Compare the silver enhanced and ethidium bromide stained gels. If the same band is stained in both, then that's the labeled oligonucleotide. To quantitate labeling, use the UV visible spectra. And here's the UV visible spectrum of nanogold. And here's the UV visible spectrum of a nanogold protein conjugate, in this case a Fab prime fragment of an antibody. If you overlay these spectra and adjust the vertical axis so that the visible regions overlap at exactly the same height, what you will find is there is a difference in the 2 traces at 280 nanometers, which is where the protein absorbs. And you can use that difference to quantitate the amount of protein, the amount of Fab prime you have. So using the extinction coefficient, you divide that difference by the extinction coefficient to get the concentration of Fab prime. Meanwhile, you take the absorbance at 420, where the protein doesn't absorb, and divide that by the extinction coefficient of nanogold at 420 nanometers, and that gives you the concentration of nanogold. And the labeling efficiency is the concentration of nanogold divided by the concentration of protein. And the link at the bottom of this slide will take you to a page on our website that gives a complete explanation of this procedure, as well as a more detailed procedure for use where your protein also absorbs at 420 nanometers. These are the catalog numbers and packaging for our 1.4 nanometer Click Nanogold reagents. And here are the catalog numbers and packaging for our 5 nanometer Click Nanogold and for our Click Nanogold reagents. For more information, please visit our website, nanoprobes.com, and follow this link for more information specifically on our Click reagents. Thank you very much for attending this presentation, and we wish you good luck and success with all of your nanogold labeling and gold nanoparticle reactions. Thank you. To contact us for more information, here are our ordering customer service numbers and emails, and our contact information for technical support. And at the bottom of this slide, use this link to download the slides for this presentation and review them at your leisure. Thanks again, and best of luck with your Nanogold labeling.